Okay, so we've talked about the two great triumphs of modern Big Bang theory, the microwave background and nucleosynthesis. Now we'll talk about some of the more embarrassing things we do not understand. And the first of them is how the universe got its lumps, how the universe became full of structure. We know that the universe, just after the Big Bang, 300,000 years after the Big Bang, was very, very uniform because we can see it in the microwave background. It was a hot glowing fog. And the height of excitement here was that this bit of hot glowing fog might be 1 part in 100,000 denser than that part.
1 part in 100,000, that's smoother than anything I can think of on Earth. That's smoother than a billiard ball by a lot.
So a package tour in the early universe is really boring. So we're going to go over here, and it's hot glowing gas over here. Hot glowing gas down here. It's hot glowing gas, but this is really exciting because it's 1 part in 200,000 denser than that bit over there. That is the height of tourism excitement in the early universe.
And the irony is that if we come to the nearby universe, or the universe of today, it looks like this. A place where there's lots of stuff, and then maybe places where there isn't so much. Even if we look around the Earth, the density contrast between the Earth and then just going a couple hundred kilometers outside the Earth's atmosphere is 20 orders of magnitude. So rather than being insanely smooth, it's insanely lumpy. How could that possibly be?
So how do we get from such a smooth universe to such a lumpy universe? Well, the normal idea is that we look at what's called gravitational instability. Let's say that we're in the early universe, it's all pretty uniform, but let's say this bit up here is just a little tiny bit denser than this bit over here, like 1 part in 100,000. So because this bit is a little bit denser than that bit, if you're an atom in the middle, which way do you go? There's slightly more mass on this side than on that side, so there's going to be a little bit more gravitational pull, so the matter will start drifting up towards here. As matter drifts into this denser region, it becomes denser still. As it becomes denser still, its gravity becomes stronger, so it sucks more stuff in. Denser still, more stuff comes in. Denser still, more stuff comes in. So the whole process runs away.
And we can simulate this on a computer. So what you do is you fill a box full of a bunch of particles and you let gravity take the things where they shall go. You calculate it between each particle. And what do you see? Well, you see this very smooth universe can collapse down into what is effectively a structure where there's lots of stuff and then voids where there's very little. Not a bad representation of actually the universe we live in.
So if we have these very small amounts of lumpiness to begin with, they will amplify themselves and become bigger and bigger. The trouble is, where do you get these small fluctuations, what we call inhomogeneities, to begin with?
So some people have an idea, and that idea is that when the universe was very young, there was lots of energy per particle, lots of energy everywhere, and you could literally form particles in and out. These so-called quantum fluctuations were coming in and out of existence.
So the early universe, there's a bit of vacuum there, would have had continuously forming particles and disappearing. These are called virtual particles, and they still occur today. This may sound like science fiction, particles, energy spontaneously appearing out of nowhere and disappearing again, but it happens routinely in laboratories, including some here at the ANU.
Hi, my name is Pinkoy Lam. I'm a professor in physics from the Department of Quantum Science. Vacuum, which is a region of empty space, is not perfectly empty nor quiet. If we believe in the quantum theory, vacuum always have a little bit of vacuum noise or vacuum fluctuations. So what we have here is an experiment that uses laser beams to amplify the vacuum fluctuation to a level where we can use standard photodetectors to detect its presence. So miniaturized version of the optics that I'm holding in my hand are found in some of the fiber optics loops on the table. These fiber optics loops are used to optically process the vacuum fluctuations.
We can take the signals that Pinkoy detects and convert them into sound so that we actually listen to the sound of a bit of empty space. And this is what it sounds like.
So we see that these quantum fluctuations are really happening in the universe today, and presumably in the universe of yesterday. But we have to make them blow up by 60 orders of magnitude to explain the lumpiness in the universe we see. Now that strikes me as a big stretch for any theory.
The way you do this is invent a new force of nature. We have a mysterious field that's sole purpose is to make the universe expand like crazy for a bit and then stop. and you finely tune it to do both of those things. This is what's called the theory of inflation. We've no evidence for this field's existence other than the fact we need something to amplify these quantum fluctuations from the size of an atom up to the size of a supercluster of galaxies. But why not? What's a new force of nature between friends? But even then we have a problem. Naively, if you take these little quantum fluctuations and amplify them up to this enormous scale, they end up about 100 orders of magnitude too big. So instead of being very slightly denser over here than over there, it's much denser over here than there. So this immediately collapses to form a black hole. So the entire universe collapses into a whole nest of black holes within a millisecond, and life can never form. If you do it the other way around, have the fluctuations smaller, which some theories also get you, then this bit is denser than that bit, but by such a little amount that basically nothing ever happens. So you have to get it just right, and that's very hard.
So this has been a huge area of research of theoretical astrophysics for the last 30 years or so. People trying to figure out what type of force, what type of field they need to invent that can simultaneously blow these quantum fluctuations up to the right scale and stop at some point, because if you keep on getting bigger and bigger, then it has to stop at some point, or of course we never form either. But at the same time, it also has to go through and get the smoothness of the universe just right. Not too lumpy, not too smooth, to have a universe where people like us can live, stars can form, galaxies can form. And that turns out to be a big ask.